Welcome to the next in the series of videos from the polymer group of the AMCASH project. In this video you'll find out more about dynamic mechanical thermal analysis and how we can use it to help your company. DMTA is a technique which combines thermal and mechanical testing. It's used to find out how a material responds to cyclic deformation according to the frequency of deformation and determines the temperature at which different changes occur. The transitions or relaxations that happen provide information about the stiffness and damping behaviour of a sample. So we know that DMTA looks at how a material responds to different frequencies at different temperatures. But how does that relate to real products in real applications? Why is it useful? Think about the rubber part of a windscreen wiper blade. Will the frequency of the vibrations it experiences when moving across the windscreen cause it to crack on a cold day? Or will they cause it to become sticky on a hot day? We can use DMTA to help determine the glass transition temperature, known as the TG, of a sample. This is an important temperature as the mechanical properties of a polymer are different above and below the TG. Below this temperature, the material is relatively inflexible, hard and brittle. Above, it is more flexible or rubbery. Knowledge of the TG can be used to inform the operational limits of a material, which may differ depending on whether the material is in use or in storage. Hard plastics are usually used below their TG where they are stiff and strong, and rubbers are normally used above their TG where they are flexible and stretchy. The data gathered may also indicate whether there has been any change in the degree of crystallinity or any degradation of the material. DMTA can be a useful technique to assist in new product development or in identifying problems with existing materials, whether that's comparing different materials or the effect of different additives or processing conditions. The image shows a sample setup for a dual cantilever testing run. This is where a sample is loaded into the frame and secured at either end in two fixed clamps. It is also secured in the centre and a clamp which moves up and down during the run. This applies force cyclically in what is known as sinusoidal deformation. As testing takes place inside an insulating furnace, liquid nitrogen can be used to lower the starting temperature, and the temperature can be raised up to 600 degrees C. A thermocouple is used to monitor the temperature as it is increased during the run. Sinusoidal deformation produces an in-phase and an out-of-phase response. The elastic response, which occurs in phase or in sync with the deformation, is called the storage modulus, and it relates to the stiffness of the sample. The delayed out-of-phase response, which lags behind the deformation force, is known as the loss modulus. The ratio of the loss to the storage modulus gives us the tan delta, which is a measure of the damping behaviour of the sample. In other words, its ability to absorb and dissipate the energy throughout the material. Changes in the storage modulus tell us about changes in stiffness, and changes in the tan delta tell us about changes in damping. With DMTA, we can see what temperature these changes happen at, and how they are influenced by different frequencies. Here at AMCASH we have an HDMA 242, capable of temperatures from -150 to 600 degrees C. Samples can be tested in a 3-point bend, single cantilever, or dual cantilever setup. Thank you for listening. If you'd like to get in touch or would like more information, please go to www.amcash.co.uk.